My name is Mafalda Moriera. I'm a first-year PhD student in physics. And today I want to talk about this topic of how we can advance flexible spintronics by using scalable topological insulators. To give you a rundown of our motivation to study this theme, we have seen in the last few years a lot of advances happening in technology, all the way from stretchable displays and bendable displays to advances in health monitoring and wearable technology, all the way to new paradigms for computation emerging through mesologic devices, neuromorphic computers, or quantum computers. And it seems that when we focus on this specific paradigm of computation, all of these advances serve to do one of three things: to make our technology either more efficient, faster, or more adaptable. When we look at these trends in research of how each of these goals is fulfilled, we can see that for energy efficiency, there's a lot of interest in advancing through spintronics by encoding using the electron spin instead of charge. For speed, we have the new possibilities enabled by quantum materials such as graphene, topological insulators, or quantum dots that can really advance speed. And for adaptability, we also have this growing interest in wearable technology like electronic skin and biosensors that can also be accomplished by quantum materials such as graphene and 2D materials. And of course, even though all of these topics find ways to intersect, ultimately, the goal is to design computation devices that can combine all of them. So spintronic devices that are highly efficient, that can adapt to wearable technology, and that are based on quantum materials for higher speed and to enable these new mechanisms for computation. And we honestly believe that topological insulators are very promising candidates to do so. For those of you who don't know, topological insulators are materials that have high spin orbit coupling, and because of this, they exhibit a unique band structure. So in the bulk, they are insulating or semiconducting. They have an opened band gap, but they also exhibit these surface spin polarized conduction channels on the surface of the material, which can be described by a Dirac cone of states. And this gives topological insulators a lot of unique properties, but on the specific application to spintronics, they're really good, particularly for spin-to-charge conversion, for detecting spin currents. So they have found a lot of applications in this field. However, even though they are highly applicable, there's still a lot of challenges to address in this research, namely having to do with finding scalable and cost-efficient fabrication methods that do not compromise on controlling competing bulk and surface contributions, because even though they are theoretically insulating, in practice, the bulk does contribute a lot to conduction and hinder the surface state contributions. And also exploring TIs for flexible applications is something that has not been accomplished yet. And that was precisely the goal of our research, to attack each of these challenges. Recently we published a paper in Advanced Functional Materials where we explored flexible bismuth telluride thin films grown through scalable methods and explored how we can really tune their properties in order to achieve these goals. And if you want to check out our article, you can scan the QR code. It came out just last month in Advanced Functional Materials. But today I will go over how what we did and exactly what makes us say that this is promising for the application of topological insulators. But before I get to the results, let me just turn on the lights for a second so you can see our graphs better. One of our goals, like I said, was find scalable ways of growing these materials. And to do so, we used DC magnetron sputtering to grow bismuth telluride thin films on flexible polyamide substrates. Bismuth telluride is a well-known topological insulator. It has high spin orbit coupling, and usually it grows through this van der Waals stacking of quintuple layers. This is our films seen up close. As you can see, due to the polyamide flexible substrate, they do exhibit a lot of surface defects because they follow the roughness of the flexible substrate. And so naturally, they're going to have some defects associated with these surface textures that you see. We grew films in different thicknesses from 13 nanometers all the way to almost 200 nanometers, as confirmed by X-ray reflectometry, to test also the influence of these different thicknesses. And we guarantee that they are stable for flexible applications by doing bending tests, where we saw that we have high bending stability as resistance increase was limited to 7% over 1,500 bending cycles. So they're very, very stable materials and flexible substrates. The other thing that we did, like I said, to try and improve these films, because we already knew that we were working with some defects, was to test thermal annealing optimization at temperatures between 100 and 325 degrees Celsius in a constant argon flux for 1 hour. We did this with all the different thickness films, and then tested how structure improves through both X-ray diffraction and Raman spectroscopy. And what we saw is really not all that surprising. So for temperatures above 275 degrees Celsius, we see increases in crystalline size and polycrystalline organization. So our films are more structured and organized in all possible orientations. And we also saw a drop in local defects as seen by Raman spectroscopy through this tuning of the Raman modes, which indicates that we are also controlling self-doping through vacancies and potential local defects in the film. When it comes to how this reflects on the electronic properties of the films, we saw a generalized drop in conductivity for all films and increases in Seebeck coefficient, even though this behavior could be explained by the formation of surface oxide layers. We believe it has to do with this decrease in bulk electronic contributions due to the control of local defects, since by analyzing the a thermal-dependent resistance of the films, we saw that for all of them, we achieved this metastable transport regime at temperatures between 20 Kelvin and 150 Kelvin, which suggests that we go from having mostly the bulk contributing to resistivity to actually seeing the metallic contribution of the surface states begin to emerge. And this is, of course, is an influence that is higher in the thinner films, which have a higher surface to bulk ratio. And so this was already a really good sign that we were starting to see the influence of the surface states begin to emerge. But to confirm this, we also did these magnetoresistance measurements on the films to search for the weak anti-localization effect, which appears below 20 Kelvin, so at cryogenic temperatures. And we can model it through a Hikami-Larkin-Nagaoka description, these cusps that appear in the magnetoresistance. And then we searched to see if we have an alpha equal to 0.5 per spin channel. So we are expecting an alpha of 1 in 3D topological insulators, and also track the evolution of the phase coherence length in these curves as temperature is increased. And what we saw is that first, starting with what doesn't change, both before and after annealing, we see that this alpha coefficient is not just controlled by the number of surface states, which we expect to see in the material, but also by thickness. And this can be explained by a bulk-mediated coupling of the two spin channels, which was also observed in a scientific report that came out in 2016 in films grown by magnetron sputtering, as you see quoted here at the bottom. So it seems that for the thinner films, we see a single effective surface channel, whereas for the thicker films, the contributions of the surface states can be completely separated. And so we have that two independent spin channels as expected. What does change? There are two main things that change in the weak anti-localization effect. The first one is that we see that the magnetoresistance becomes stronger. So the signal that is emerging from these surface states is also becoming stronger post-annealing. And then by tracking the phase coherence length, what we see is that before annealing for the as-grown films, if we analyze the decay rate of the phase coherence length, we get values between 0.6 and 0.7, which is consistent with having 3D electron interactions as the main dephasing mechanism, which would be indicative of having mostly bulk contributions to this effect. Whereas after annealing at 300 degrees Celsius, we saw that this decay rate grows closer to 0.5, which again is indicative of having 2D electron-electron interactions and hence mostly contributions emerging from the 2D surface states. So these were very encouraging results, and in future work we hope to apply them not only to other materials, but to start by testing this annealing time dependence of the thicker films. I don't know if you noticed that for the 200 nanometer films, we saw this deviant behavior. The electronic properties didn't evolve as much as we had hoped. So we will also be testing higher annealing times to see how this influences the structure of the film. We already have some structural results from transmission electron microscopy, which is what you see here on the left, and Raman spectroscopy, but we will be conducting a more thorough study on this end as well. And then also applying this to other TI materials to see if the study is reproducible, and testing their efficiency for these spintronic effects by building TI-based heterostructures and devices. So these will be all goals that I'll be pursuing throughout my PhD. And just to conclude on this presentation, I hope to have convinced you that there's still a lot of work to be done in this field to control the unique properties of topological insulators, but there is no reason why we shouldn't try scalable methodologies and growing these films on flexible substrates. This is a very rich field to explore. There is a lot that we still don't know. And we hope that in the near future, what we have accomplished so far will help us understand the contributions of these complex quantum phenomena in flexible TI and also develop more complex structures. Thank you very much for your time, and we will be taking questions.
So thank you, Mafalda, for your presentation. Very, very, very nice presentation and very nice summary. So do we have any questions from the audience? We have time for a few questions. So if you have any questions, just unmute yourself and just ask them right away.
Hi, Mafalda. That was a nice presentation. I just wondered
Thank you.
how you did make sure that there were edge states in this kind of material. I think you mentioned it's probably in
Right.
the second point, right? The
Yeah.
presentation.
That is a very important question, and thank you for asking it. Because in reality, right, the only way to directly measure the surface states is to do angle resolved photoemission spectroscopy. So in that way, we would be directly measuring the band structure of the materials, and we would be able to see the Dirac cone emerging in the band structure. And that would be the ideal scenario, right? Because we don't have access to high synchrotron facilities every day. What we do is we try to search for other ways that the surface states can emerge. And one of those ways is through the weak anti-localization effect. So we know that this effect is expected in TIs. Its emergence doesn't mean directly that we have edge states, but if we see that its description is very close to this theory of the Hikami-Larkin-Nagaoka model, then we have strong conviction to say that they are there.
Yeah, all right, that makes sense. Me too, I was thinking about the band structure, but yeah, that's kind of supporting the idea.
A little bit harder to...
Yeah.
Oh. So I guess we will be like short in time. Thank you, Mafalda, for your presentation. And please just be present in the Gather Town to receive like other questions and discuss with